Starting, test, test. Test. Test, test. Hello, and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate in the Material Science program at the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and also university level. So if you need any help with homework or if you needed tutoring help, just click on the links in the description below, and I'll just go get started with the first set of questions. Okay, so the first question asks, a neon lamp produces what kind, I'm assuming light, on the visible spectrum? Okay, so let me just write down. This is question number 1. So basically, I'm just going to give a rundown of the different classes of spectra we can have. So you can have 2 distinct classes of spectra. So the first one is continuous. And with continuous spectra, you tend to see a wide range of colors / energy. And the second class of spectra is called discrete. So with discrete spectra, you only see bright or dark lines at like more distinct or defined colors. Okay, so that's a general overview of the types of spectra you could have. So basically for neon is what this question is asking. Neon only emits certain wavelengths that are specific to different atoms in the bulk. So I'm just going to write that down. So it only emits blanks specific to the atom's bulk. So also for neon, there's little or no wavelengths in between. So it tends to radiate in both the red and orange area in the visible spectrum. Okay, so therefore the emission spectrum is discrete for neon. Okay, so again, since neon doesn't give a wide range of different colors and energies, it's not a continuous spectra, and it's known as discrete. So it tends to radiate light in the red and orange area. So let's just confirm with our answer. So neon lines radiate in the red and orange area of the visible spectrum. Mostly depends on what type of other gases. Okay, so when other gases are used with neon, then the mixture can radiate in all types of other colors. Neon light can only happen at a few individual energy states, and the amount of excitement of the electrons, and most of these are located in the red, with a few in orange and yellow. Okay, so I'm just gonna verify this solution. Answer is correct. I'll also add that the emission spectra for neon is discrete and not continuous. Oops. So the solution is correct. Okay, so that was question 1, and on to question number 2. So question 2 states, which of the following solutions will have the highest electrical conductivity? Okay, so let me write down the definition of what we're looking for in electrical conductivity. So basically in this question, they give us different concentrations of different solutions or electrolyte solutions. So for this question, electrical conductivity means that it just conducts electricity. And what we're looking for the solutions is the highest concentration of ions. The aqueous solution. So just go over each solution and try to calculate its concentration of ions. So the first one is 0.10 molar of potassium iodide. So if you were to break up this potassium iodide to its ions, you would get A plus, I minus. So therefore, the number of ions, so I'll just denote it as I, is equal to 2. And then we also want to take account its concentration. So you have 2 ions times the concentration, which is 0.1, molar, and you get a concentration of 0.2 molar of ions. So that's for A. And then we can do the same thing for B. So B is 0.05 molar carbonate. Okay, so I'm going to calculate the number of ions. So there are 2 NH4 plus ions and 1 CO2 minus. This gives us 3 ions in total. Its concentration is 0.5 molar times 3, and you end up with 0.15 molar for this solution. On to C, 0.10 molar potassium fluoride. The number of ions again is 2. So this gives us the same answer as the first one, 0.2 molar. For D, you have 0.045 molar aluminum salt. So for this solution, I have 2 aluminum ions. Oh, I forgot to put the 3 SO4 minus ions. So in total there are 5. And I multiply this by the concentration. I end up with 0.225 molar. So far this is the most conductive. I'm just going to look at the last one real quick. 0.1 molar KBr. So this is the same as the first one again. You get 0.2 molar of ions. Okay, so just looking at all the different concentrations we calculated, we can say that this D solution is the most, has the highest electrical conductivity. So let's just look at our answer. They also calculated the different moles of ions, and they got D because conductance depends on the number of ions. So let me just verify. The solution is correct. Okay, so on to question number 3. Construct the molecular orbital diagram for H2+, and then identify the bond order. Make sure you add electrons to the boxes corresponding to the molecular orbitals for the molecule and to the boxes corresponding to the atomic orbitals for the 2 atomic species. Okay, so I'm just going to write on the side. First, the molecular orbital diagram. So they already kind of gave us the basic skeleton, but if you don't remember or if you are confused with how to construct diagrams like this, basically you have your y-axis which is energy, and the more you go up, there is a higher amount of energy. Okay, so first you draw the different atomic orbitals. So you always start off with 1s for this hydrogen species. And since there's 2 of them, I'm going to write them on either side. And then when there's hybridization, you have your sigma 1s, and then your sigma star 1s. So this is bonding and anti-bonding. Then I'm just going to draw these lines to and I'll do what the question did. So these 2 levels correspond to the atom. And then the middle one is for the molecule. And for this question, our atoms are 2 hydrogens. And our molecule is H2+. So before you fill out your energy diagrams, you want to figure out how many electrons are involved in this molecule. So each hydrogen gives 2 electrons. So we have 2. But since there's a positive charge, that means that one of the electrons was removed. So we're going to do 2 minus 1. So we should have 1 electron total. So the next thing I'm going to do is I'm going to fill in my diagram. So I'll show that 1 electron is in the atom. And for the hydrogen that lost an electron, I'm not going to write anything there since it was lost. And then finally, I'll write that only 1 electron is involved in the bonding. So this is what our diagram looks like. It's pretty simple. Hydrogen is one of the easiest elements to write with a molecular orbital diagram. But as the compounds get more complex, you tend to have different levels, and it gets more complicated. But in our case, this is just a simple molecular orbital diagram. So the next part of the question says to calculate bond order. So I'm just going to write down this equation for bond order. This is the number of electrons, the bonding, minus the number of electrons, anti-bonding. I'll just put anti-B. All of that divided by 2. This is BO. So in our case, we have 1 electron in the bonding, and we have 0 in the anti-bonding, so that's sigma star. Divide that by 2, and we get a bond order of 0.5. So I'm just going to confirm and verify with the answer given here. Okay, so the answer given here is a different, yeah, so this is H2 and not H2+. So this particular answer is correct, but since the question that we're looking for is for H2+, it would be missing an electron, and the bond order would be equal to 0.5. So I'm just going to write that down. so this solution is correct for H2. However, for H2 plus, an electron is removed. So I'll just say the solution is incorrect for this particular question. Okay, so the next one. Now we are on question 4. The molecule cyanazine, once used as a herbicide, has now been phased out by the EPA because of its significant human toxicity. Add lone pairs as needed to the structure of cyanazine. Also indicate the hybridization of the specified atoms. So first I'm just going to write down the structure given for cyanazine. It's a very large structure, so bear with me. Chlorine. So this is the full structure of cyanazine. And the first part of the question wants us to add lone pairs. So I'm just going to add them for our nitrogen groups. Just give lone pairs all around. So that's for all of the nitrogens. I'll write it all for the chlorine as well. So that looks about right. And then I'm going to number my carbons the same way they did in, my carbons and nitrogens the same way they did in the question. So this was 1, 2, 3, 4, and 5. So next I'm just going to write down a way that I try to remember different hybridizations. So for this question, I'm just going to write down the 3 that we're looking at. sp3, sp2, and sp. So with sp3 hybridization, your atom is connected to 4 charge clouds. So basically a charge cloud can mean either a lone pair of electrons, or it can mean like a bond to another atom. sp2, 3 charge clouds, and sp is 2 charge clouds. So I'm just going to say charge clouds and be either a lone pair or an atom. Okay, so first let's look at our first nitrogen. It has 1, 2, 3 atoms and also 1 lone pair. So that means it has 4 charge clouds. And this nitrogen is sp3. For number 2, This nitrogen has 1, 2 atoms and 1 lone pair. So that means it has 3 charge clouds in total. So that nitrogen is sp2. Next, let's look at this carbon. I have 1, 2, 3 atoms. So this carbon is also sp2. For 4, you have 1, 2, 3, 4 atoms. This is sp3. And lastly, for this last carbon, there's only 1, 2 charge clouds. And this is sp hybridization. So another thing I noticed, if you don't want to do this charge cloud way, is that basically if there's single bonds involved, it's sp3. With double bonds, it's sp2. And with sp, it's triple bonds. Now let's look at our answer. They drew in all of the lone pairs in the right places. Lone pair in 3 bonds, sp3, sp2, sp2, sp3, and sp. So this solution is correct. Okay, so now on to question number 5. Give IUPAC names for the following compounds. So the first one, the answer is already given. It looks like they just want us to answer part B. But I'll still try to talk you guys through on how to answer part A as well. So let's pretend like I didn't see what this answer was. And I'm just gonna write down the structure for part A. Got a triple bond here. Double bond here. Oh, another. Okay, so the first thing you want to do when you want to try to name compounds like this is to think of what my teacher told me was called the parent rule. So basically what the parent rule states is that the longest chain of most important things will be your parent. And also when you want to name the carbons, you want to have the lowest amount of numbers possible. So this will make more sense once I try to name this compound. Okay, so let's look at this structure. It's got 2 double bonds and a triple bond here. And I'm just going to start numbering the carbons. So 1, 2, 4, 5, 6. So we have 6 carbons in total. Then I'm also going to write down the prefixes that are involved in this question. So it's always important to memorize these prefixes, especially when you name. For 1, it's meth. 2, eth. 3, prop. 4, 5 is pent, 6 is hex. I might as well just write the other ones. 7 is hep, 8 oct, 9, 10 is dec. So these are all the different prefixes, and the first thing I like to do is to notice that this whole thing can just be like a parent, and since there are 6 carbons, I'm going to write hexa. So on carbons 1 and 3, there is a double bond. So in order to say that, I'll say 1, 3. Since there's 2 of them, I'm going to write di N. So for N, that means there's a double bond involved. And to show that I have a triple bond here, I'm going to say carbon number 5, there is a triple bond, ene. So if you're wondering where I got that N and the ene from, for alkanes, these are single bonds. Alkenes, N, are double, and alkynes are triple. And that's how you get the answer 1, 3 hexa, which is our parent, di N 5E. So if we were to number it the other way and made this carbon 1, 2, 3, 4, 5, 6, then it would be 5, 6 hexadi and 1 ine. So again, you want to have the lowest amount of numbers, so that's why I numbered this carbon as 1. So now we can go to part B with this long structure here. Just gonna start a new page. It's pretty big. So this is also question 5. Continued. You have a carbon that has these methyl groups sticking out. Have one with a single methyl group, carbon with a triple bond, carbon with 2 methyls, one that just has CH2, then ends with CH3. So again, with the parent rule, we want to find out which chain has the longest amount of all the important things. So I'm just going to circle the parent. It starts from here, and this whole thing is our parent group. Then I'm just going to circle all of the different side groups. We have 2 methyls here, there, there, and there. And now I'm going to number my carbons. So this is 1, 2, 4, 5, 6, 7, 8. Okay, so our parent has 8 carbons, so it will have oct. And then the first thing I'm going to do is to look at all of the different methyl groups that are here. So I'm going to do the triple bond last. Basically, you want to do this in alphabetical order. And since it ends in "-ine", Y is last. So I'm just going to say this will end in "-ine". So this just shows that there is a triple bond on carbon 4. So next, I'm going to write down all of the carbons that have our methyl groups on it, but I'm also going to specify which ones have 2. And in order to do that, you have to basically write the carbon number twice. So since carbon 2 has 2 methyls, I'm going to do 2, 2, 3, and then 6, 6. Penta methyl, bitch fix. Okay, so our answer for this question is 22366 pentamethyl oct 4-ine. Let's look at the answer. So they wrote it down, 22366 pentamethyl oct 4-ine. So solution is correct. Okay, so on to question number 6. So the formation of hydrogen bonds requires hydrogen atoms and what else? Water, oxygen, ionic bonds, or polar covalent bonds. So we know the answer is not A, and that's just because you don't always need water to form hydrogen bonds. Same thing for B. You don't need oxygen to form hydrogen bonds. And for C, it's also not C because ionic bonds, they contain a metal as well. And when you form hydrogen bonds, ionic bonds are with metals. So I'll just explain what hydrogen bonds are after. So our answer is D. Polar covalent bonds. I'll explain why. So people tend to get confused with the word like hydrogen bonding. They think that just because there's a hydrogen involved and it's connected to something else, this is what a hydrogen bond is. But I'll just write down the definition of hydrogen bonds. So hydrogen bonds are weak bonds, and they result from an electrostatic attraction between proton, is also just H+, and an electronegative atom. So I'm just going to do the easiest example to show what hydrogen bonds are, and I'm just going to use the water molecule. So here's the water molecule. Everyone knows is H2O. So our oxygen is more electronegative. So I'm going to show that using this arrow. So since our oxygen is more electronegative, it has a slightly negative charge, leaving our oxygens to have a slightly positive charge. And basically with hydrogen bonding, this is what happens when that slightly negative oxygen has an attraction to another water molecule that is slightly positive. So basically this attraction right here is what hydrogen bonding is. So therefore the answer is D. You need polar covalent bonds. So polar covalent bonds are between two nonmetals. One of them is more electronegative than the other. In this case, our oxygen is more electronegative. You have a partially negative charge that is attracted to a partially positive charge on a different molecule. So let's read what this answer says. Hydrogen bond is an intermolecular attraction force between two molecules, as one of the atom is hydrogen or other electronegative atoms. Due to the presence of the polar bonds, a molecule behaves as a dipole. Hydrogen of one molecule exerts the attractive force on negative charge center of another nearby molecule. So this solution is correct. So that question wasn't so bad. So now we're on to question number 7. Draw the structural formula for the major product of the acid-base reaction shown below. So first I'm going to write down the reaction. Have an let's fix that. I'm so bad at writing hexagons. That looks weird, but so basically we have this molecule reacting with only 1 mole of HCl. So this is an acid-base reaction. So our base is this large molecule. Our acid is hydrochloric acid. And with acid and bases, the acid is the proton donor and the base is the proton acceptor. So basically we have 2 nitrogens on this molecule and each of them can act as a base, but since there's only 1 mole of HCl, we want to find out which one of these nitrogens will successfully take that proton. So which of these nitrogens is more basic? I'm just going to write that down. To quantify the basicity of an amine, we want to look at the pKa of its conjugate acid. So again, to In order to find out which base is stronger, we want to look at the pKa of its conjugate acid. So I'm just going to draw out what these conjugate acids may look like. So in the case of pyridine, which I'll draw here, it will look like this. So that's the conjugate acid of pyridine. And for the primary amide, I'm just going to shorten this as R. If it were to accept the proton, it would kind of look like this. So another way you can call the pKa of a conjugate acid is to just call it the pKaH. And basically the trend for this is that the higher the pKaH, the stronger the base. So I know it's a bit confusing. So again, pKaH is the pKa of the conjugate acid of these bases, which I drew here. And basically, the higher the pKaH, you get a stronger base. So the stronger base will be able to deprotonate this 1 mole of HCl. So just to save us time, I looked up what the pKh of these bases were. For this one, it was around 5.2. For this one, it had a pKh of negative 0.5. So since the amine that is in the pyridine group has a higher pKh value, that makes it the stronger base. So therefore it's able to deprotonate the HCl. I can write our final product here. It'll have a positive charge. I'll just draw in the double bonds. Then this amine remains the same. And then, even though I don't have to include those ions, just write Cl minus there. Okay, so this is our final product. So it's the same. So this solution doesn't really look like it answers the question. Yeah, this looks like a different answer altogether. I'm just gonna write down the nitrogen in the ring will deprotonate HCl since it is a stronger base. Okay, so I think I have time for one more question. So this is question number 8. Below are shown structures of 4 possible bromination products of toluene. Indicate the product or products formed in significant amounts when bromine reacts with toluene under each of the following catalytic conditions. So the first condition is Br2 in the presence of a peroxide catalyst, and the second was Br2 in the presence of FeBr3. So let's do A first. So basically the toluene molecule looks like this. There is a methyl group there. And the first instance is Br2 in the presence of a peroxide catalyst. And usually with this reaction, you need UV light. That's not answered in the question, but I'm just going to add it there. So when you have Br2 and peroxide and UV light, I'm not going to draw out the mechanism because it's really complicated, but basically you end up with a structure that looks like this. So this is our carbon that is here. And this reaction, the mechanism occurs through a free radical process. I'm going to rewrite that here. So this occurs through a free radical process. Basically, you need UV light for these types of reactions because you really need to add more energy in order to have reactions that occur through the radical process. And what's cool about this reaction is that the bromine is attached to the carbon that is least substituted. So we call this Markovnikov. Just label this as benzyl bromide. So since this is an anti-Markovnikov addition, it's not that favored if the UV light and the peroxide weren't there. So this is the final product that we get for part A. For part B, we're going to do the same thing. Write down toluene. And this time, it's Br2 in the presence of FeBr3. So for this question, it's just a standard bromination. So you can have bromine either on this carbon. So this is the ortho position. Or that was a really. Or you can have the bromine down here. So this is the para position. So this process is the opposite of the other one. This is a Markovnikov addition. And again, what this rule means is that it adds in the most substitute. So in this case, it was this carbon and this carbon that are more substituted than this carbon that only has the 3 hydrogens. So let's look and confirm our answer. Oh yeah, let me just write down what letters these are. So for this is the same thing as product A. This is product B, and this one is product D. So for part 1, this is peroxide. This because peroxide encourages the formation of benzyl free radicals, which is highly stable. 2 is B and D, yep. This is electrophilic substitution, and the CH3 is ortho-para-directing. So B and D are formed. D is formed in a higher quantity than B because of the symmetry. So I didn't add that, so it's a good thing to note. So this D will be formed in a higher quantity, again, because of its symmetry. So I'm just going to confirm that the solution is correct. Okay, so those are all the questions that we have time for today. I hope you enjoyed today's question and answer segment. And if you'd like to be notified of when we do this next, then hit the subscription button below. And also, if you like this video, leave a like and a comment. So if you'd like to submit your own questions, visit the links in the description below. And this has been Donna and from the OneClass community, and I hope to see you soon. Goodbye.